Okay, now welcome back. Right now, the thing that we just plan to do is, again, we are still at the phase that we just want to assess the convergence of the algorithm that we had for the stand modeling. Before, if you remember, on the previous tutorial that we had, we just said, okay, for each parameters that we defined for our model, we just come to just do a kind of, I should say, a diagnostics. And that it was a reason that we just did all these, I should say, the plots. However, the thing that we can just do is that it's going to become very simple in case if we just want to use, I should say, the function which is called the trace plot, which you will see that the trace plot essentially is a function which comes when you have just R stand installed on your R. And as you can see, it says that the trace plot corresponding to one or Markov chains, and I should say that's a visual way to inspect the sampling behavior and assess mixing across chains and the convergence. And that's the thing which you just want to do. I assume that you have your R stand installed in your system, and still it has, I should say, the tick next to that, which means that that's ready to use. Now we're just going to go ahead and just use the trace plot. Somehow, if you are just going to use the trace plot for the first time, the thing that we do is that for the trace plot, we just press the F1 to just have the help menu open here. Okay, for the first thing that we need to just, I should say, the object, which is going to be of the class of the stand fit. Because if you remember, for the model that we had, for the model, we just said that the class of the model, it was, I should say, the stand fit. Then as a result, for the trace plot, if I'm just going to use the stand fit, I simply come here and I say that, okay, it's going to be, I should say, the model A, trace plot. I'm just going to go with the model A, and it's going to be one of the objects. This object is one of the crucial objects that you have to just introduce that inside the parentheses for the trace plot to have your analysis to keep running them. However, I'm just going to go ahead to just go to say that, for example, you have for many other options that you can just choose. For example, you have the option which is going to be the parse. For the parse, essentially, if you just want to introduce the parse, the thing that you do is that you just come here to define as a combinations the parameters that you just want to have diagnostics with. For example, imagine that at this stage, I'm just going to only go to choose the parameter, for example, for the alpha. What was the alpha? If you remember, the alpha, it was a parameter that we defined that, which defines the slope of our linear model for, I should say, for the one which we defined. However, the alpha is, we call that in the stand, we call that alpha. We had that in our model as A, but in the stand language, we just introduced the alpha. Okay, imagine that you are looking only for the alpha. And also, the other thing that sometimes it's good to just note that is going to be incorporation of the warm-up sampling that we had. Because you remember, on the model that we just run, for example, we said that for the number of the iterations, we had at least half of the number of the iterations for the warm-up. And that was the time that the algorithm was searching for, I should say, for the gradients, I should say, that in order to just converge. And now, in that case, normally we have the default, that's going to be a default parameter into our model. If we just have the incorporation of the warm-up false, it means that those, I should say, those samplings that we did before, before we just find the right direction in, I should say, in the gradient of the model, it's going to be incorporated, if that's going to be true. If that's going to be the false, then it means that the warm-up sampling that we did, it's going to be, which essentially it was at least the half of the number of the iterations, it's going to be excluded when you just do the, I should say, the trace plot. Now, essentially, right now, I have all the required, necessary arguments for the trace plots function in order to execute that. And in order to execute that, I'm just going to go ahead just for the parameter of the alpha. Then you see that the parameter of the beta, which relate to the intercepts of the model, and also the sigma, which essentially was, I should say, a parameter for the dispersions around the mean, they are not included in my trace plot. I'm just going to do that in the, I should say, after this, but for demonstrations for the simple one, I'm just going to go ahead for the trace plot of the alpha prime method. I just press Control Enter, and you see that the trace plot is executed. Now, I'm just gonna I zoomed the plot. You will see that at the trace plot we have 4 different colors for each different chains. Because you remember, we were able to manipulate the number of the chains when we wrote the stand function. When we wrote the stand functions, we have the argument which is called chains. We can just choose 1, 2, 3, and 4. If we just go to the 4, the probability that we just converge is going to be much higher, because in parallel we have 4 algorithms try to converge at the one, area in the parameter space. Now, I have you see that for each chain I have different colors, and this one, which shows that the wiggly and the zigzag, things that you see, everything just comes superimposed on the top of the other chain. It's sign that that the algorithm has been converged. Okay. Also, we are just going to have another, trace plot for the model bad that we had, which we didn't converge. We had the divergence, and we're just going to compare that to the same thing that we had. However, before we do that, you remember that on the x-axis, you have, 1,000 iterations that we talked about. You see that from 0 to 500, we do not have anything. We do not have any trace plots, because we put the arguments for incorporations of the warm-up sampling equal to false. Then, as a result, you see that from, iterations from 0, which is going to be here, all the way to the 500, there is no trace plot, plotted on this plane. However, also, you see that, and the alpha is going to be, that's the inference that we have for the alpha. You remember, if we just go back, to the functions, and if we just go for the posterior, and if you just go for the alpha, you see that there is 1,000th range of the samples that we got, which it ranges, for example, from, you have 26, 28, and that's why you see that the alpha, which is the result of your estimates for the slope, it's going to be taken, let's say, from, for example, from between 20 and all the way to the 30, and that's the value for the alpha, which are, dynamic Hamiltonian Monte Carlo for each sample which we draw from, the posterior distribution. From each draw, we got 1 estimate, and that's why you see that. In the next tutorials also, remember, we have to take the mean of these alpha inferences that we had in order to just make the best estimates. We are not there yet. I said that to just, to warm up your mind for the next tutorials then. Now, the thing which I'm just going to do, I'm just going to show you something different. Also, you see that if for the incorporations of the warm-up, if I put the argument as true and execute the line, you will see that how the plot looks like. I'm just going to zoom it. You see that before the 500, you see that the convergence happened, somewhere much earlier. And now that's a good picture. You can see how the convergence and how the divergence looks like from the, from the trace plot. Look at that. The warm-up sections from the iterations from 0 go all the way to the 500. You see a kind of a dark blue or dark gray, a kind of a gray color, which divides the plane with 2 different colors. And from 500 all the way to the 1,000 iterations, although you could have chosen 2,000 iterations, but there was no need, you see that there is a different colors on the plane. You see that around, somehow between, around before 250, that the chains, they have not converged. You see that how the divergence looks like. Any, any samplings which it shows from the plots of the chains, it's different. It's not superimposed as the zigzaggy and the wiggly shapes that we have over here. And you can see that if the convergence doesn't happen, how does everything looks like on the, on the trace plots. And that's one thing that it was good to see that. And now the thing which you see essentially is the incorporations of the warm-up samplings, even those samples that we have not converged with them yet. Okay, this plot looks spectacular, and you see how beautiful they look. And now, the other thing which I just want to show that I said that with the parse, you can specify to the stand for what parameters you are interested to check the convergence. Here, for me, it was important to check the convergence for, let's say, the alpha, in case if I'm interested to check for the convergence of the beta, which beta refers, I should say, to the b in my linear model, which refers to the intercept, I can just put, I should say, in the combinations for the parse, also include the beta. And I'm just going to execute the line. Let's see what do we get. We get two plots. I'm going to zoom this. You see that, for example, for the alpha and beta, you see that how the convergence happens, and you see that also for the beta, the convergence happens way before, I should say, we just switch to the initial 500 that we assigned for the initial warm-up. You can see that if I just put it as a false, which I exclude the warm-up, I should say, the samplings, you see that how the trace plots looks like, which it shows that the model has converged for two parameters, which is going to be alpha and beta. Okay, now we had another parameter, if you remember. The other parameters that we had, it was a parameter of the sigma, which it was essentially a measure of the, I should say, the dispersion around the mean of our method there. Then in order to just go ahead, I can just go and also include the sigma in my parameters, and you see that. Let's go ahead and execute the code and see how the things looks like. And you see that also with the incorporation of the sigma, we had alpha trace plot, we have beta trace plot, and we have sigma trace plot. You see that all of those three parameters, they have fully converged after the initial warm-up. And if you just want to see also their warm-up for all those three plots, you can just put the incorporation of the warm-up true in the trace plot. Then you see these kind of plots, which is very interesting, which it shows that all three plots for all three parameters, even way earlier before the 500 initial warm-up, all of them, they have converged. And now, as what we see, it's a kind of a green light that we can just move on to the next stage of our analysis, that we can just reliably make the best estimates for our parameters and also make the inferences for our hypothesis that we're interested for. And that's a step, as you notice, it's going to be incredibly important, which it showed the convergence. And it's a green light for us. But however, there is one more thing that we're going to talk about, the convergence method, which is going to be the R statistics, which is also the second way as a complementary way to trace plots. When we come back, I should say, on the next tutorial, it's going to be a very brief tutorial to talk about the R statistics, because we're just going to talk about the package, which is going to be Shiny Stan, which I like that package personally very much. Then when we just come back, we're going to talk about that methodology to check the convergence of our algorithm in the Stan. Then when we are done, we just move on to just find our best estimates and to visualize the uncertainty of the model that we are just going to be talking about then. Okay, now by saying that, this tutorial is going to end, and as I have always said, and I would say again, I can't wait to see you on the next tutorial then. See you later.